What's up, geometry students? Today we're going to look a little bit at independent events. So independent events are events that don't affect each other's probabilities. So do not affect each other's probabilities. So the one happening has no effect on the other happening. So a couple examples of this. If I were to flip this coin, I got heads this time. So the probability of me getting heads that time was 50% or a half. Well, if I go to flip it again, what's the probability I get tails this time? Well, do you notice what happened last time actually has no effect on the probability of flipping heads or tails this time? And so this time, I still have a 50-50 chance of getting heads or tails. And so what happened previously has no effect on what happens this time. Those are independent events. Independent means not related to each other, means one doesn't affect the other. Let me show you another example. So I have this little bin full of a bunch of little fuzzballs. In here I've got 2 blue ones, 3 orange ones, and then I've got 3 yellow ones. All right, so if I said, so that gives us a total of 8 balls in here, and I said, what's the probability of me picking a yellow one out of here? Well, we had 3 yellow ones, so the probability of me picking a yellow one is 3 out of 8. And so let's just pick a random one, and let's see, I got a yellow one that time. Okay, so I picked a yellow one. Now here's where things are going to get different. I'm going to take that yellow one, throw it off to the side. All right. So now, if I say, what's the probability of picking a yellow one? Do you notice now I have 2 yellow ones out of the 7 in there? What happened the last time just changed the probability of what happened this time. So I would call those two things dependent events. They do affect each other's outcome. So picking a yellow the first time had an effect on the probability of picking the yellow this time. These are dependent events, the opposite of what we're talking about today, independent events. I could make this same experiment come out as independent if, after I drew this yellow one at first, I just put it back, shook it up. Now the probability is still 3 out of 8 like it was before. And so there's this idea, sometimes it's called with replacement or without replacement. So if I replace the thing I drew before I do it again, then the first outcome has no effect on the second outcome. However, if I drew that yellow one and I leave it out, now what happened the first time has an outcome on the second time. And so that's kind of the difference between independent, do not affect each other, and dependent, do affect each other. So that's a couple important ideas for today, independent and dependent events. We're looking at what happens with independent events today, and then how we use that, how we come up with some equations, formulas, whatever you want to call it, to figure out how that affects things. So one big one we're going to use today is this right here. And remember, this little guy right there, that like upside down U looking thing, means and. So the probability of A and B, if the events are independent, is the probability of A times the probability of B. So we just multiply the two probabilities together. So let's see if we can put this to use on an example here. What's the probability of flipping heads and then tails on a coin? So you flip a coin once, you get heads. Second time you flip it, you get tails. What's the probability that this happens? Well, there's 2 ways to do this, and we kind of did this first way already, this unit. It's a good review of how this works. We could make a thing called a sample space. Now remember, a sample space is just listing all the possible things that could happen here. So here's what could happen. We're flipping a coin, then flipping a coin again. We could end up getting heads the first time, heads the second time. We could end up getting heads the first time, tails the second time. We could end up getting tails the first time, then heads the second time. Or we could end up getting tails the first time, tails the second time. So there's 4 possible things that could happen here. So what's the probability of flipping heads, then tails? Do you notice heads, then tails is just this one right here out of the 4 things that could happen? So looking at it from a sample space perspective, we could see the probability there's 4 possible outcomes. One of those is what we wanted to happen, the desirable outcome. And so the probability is 1 out of 4, or 0.25 or 25%, however you want to say it. All right, now another way you could do this, let's do it according to this formula. So this says the probability of A and B is the probability of A times the probability of B, or the probability of flipping heads times the probability of flipping tails. Now the probability of flipping heads is 1/2. The probability of flipping tails on the second flip is 1/2. Now this is a good reminder of how to work with fractions. If we're multiplying fractions together, remember we multiply just straight across the top, straight across the bottom. So 1 times 1 in the top is 1, 2 times 2 in the bottom is 4. So the probability using that formula still came out to the same thing, which is good. It should come out to the same thing, 1/4. All right, now the reason I wanted to show you this, I wanted to show you kind of like how this works, what's really happening here. But this sample space idea would always work, but it's not always convenient. Actually, sometimes it's really inconvenient to do this whole sample space thing. So let's look at an example where you would not want to do this. So this example here, if you roll a 6-sided die and then draw a card from a standard deck. Now remember, a standard deck of cards is 52 cards. And if you need a little help on what a standard deck of cards looks like, I put a standard card deck reference on Google Classroom that you guys can pull up, and it has all the information about how the different suits and colors and face cards and all that stuff works. So if you roll a 6-sided die and then draw a card from a standard deck, what is the probability of rolling a 5 and drawing a club? Well, let's just figure out each of these probabilities by themselves first, and then see if we can figure out the probability of the and, of both of them happening. So probability of rolling a 5 on a 6-sided die. Well, if there's 6 sides, only one of those sides is a 5, then the probability of rolling a 5 is 1 out of 6. All right, now for the drawing a club, we need to figure out how many clubs there are in a deck. So number of clubs we have is 13. And like I said, if you didn't know that, refer to that standard deck of cards reference I gave you guys. Out of 52. Or I'm going to simplify a little bit here because 13 over 52 simplifies quite a bit. This is 1/4. So what is the probability of rolling a 5 and drawing a club out of the deck of cards? Well, since these events are independent, now let's think for a second, why are they independent? If I roll a die, does what I get on that die have any effect on what card I draw from a deck of cards? Do you notice they're completely unrelated, right? They're independent of each other. And so for independent events, if I want an and probability, I multiply the two probabilities together. So that's what I'm going to do here. The probability of getting a 5 and a club, so I'm just going to say it like this with our and symbol, is 1/6 times 1/4. And 1/6 times 1/4, if I multiply these out, remember multiply straight across for fractions, we get 1 on the top, we get 24 on the bottom. So there's a 1 out of 24 chance that if you roll a die and pick a card, that you're going to roll a 5 and then pull a club out of that deck of cards. Now, let's think for a second why we would not want to make a sample space on this one. We could, and it would work, but it would be super annoying. Because here's what we'd have to do. We'd have to make a sample space of all the things that could happen. When we roll the die, we could get a 1, 2, 3, 4, 5, or 6. So we got 6 possibilities there. But we'd have to put every single possible card that could come as a result of each of those rolls. And so we could have 1, and then ace of spades, 1, ace of diamonds, 1, ace of clubs, 1, and then you could just keep doing that forever. And so beside the 1, you'd have 52 options. Beside the 2 that you rolled, you'd have 52 options. Beside the 3, you'd have 52 options. So if you did this, let me just multiply this out here, you'd end up with 312 things in your sample space. I don't really want to write out 312 things in a sample space, and I'm never going to ask you guys to do that, because why would you? When we have this way to do it where we don't have to do that, if it's a really small thing like this, that's not so bad. There's only 4 options of things that could happen. 312 options of things that could happen, not a good idea to try to make a sample space. All right, so is that making sense so far with the idea of independence and the fact that if things are independent, for an and probability, just find the probability of each, multiply them together to get the probability that they both occur, or an and probability. All right, and then the other thing that I wanted to do a little bit with this today is I wanted to talk about how this works on a two-way table. And so we're going to look at a two-way table here that has to do a little bit with something that I find enjoyable, which is Nerf wars. So we're going to see if we can figure out the probability of, or we're going to see if things are independent if we're talking about liking Nerf wars, not liking Nerf wars, and your age. Are you under 10 or over 10? And we're going to go with actual physical age, not how old you act like you are, which is good for me because I tend to act a little younger than I am probably. So Nerf war, for people under 10, we have 36 who would prefer to have a Nerf war. We have 12 under 10 who would prefer not to have a Nerf war. And so that makes our total 48. So remember how these things work. These total columns just add up the vertical columns and the horizontal rows, and then that means right down here there was a total of 108 people surveyed. Alright, so my question is being over or under 10 and your preference for wanting a Nerf war independent? Does it make a difference whether you're over 10 or under 10 for your preference for Nerf wars? So we're going to have to do a little math here to figure this out. So let's do a couple of probabilities and see what we come up with. So preference for Nerf war. Now do you notice this is not given that you're in a certain group, this is just overall. So preference for Nerf war is 81 people have a preference for Nerf wars out of everybody. So if we just look at people who like Nerf wars, there's 81 of them out of the 108 people. So let's see what this is as a decimal. Now you could simplify this fraction if you prefer. I'm just going to get it as a decimal because I think it might make life easier. And this comes out to 0.75. Or if you like percentages, a 75% chance. So there's a 75% chance that if you ask somebody, they would prefer to have a Nerf war as opposed to not having a Nerf war. So let's compare that with what happens if we say, what's the probability that you would like a Nerf war given that you're over 10? Remember from what we learned in our last lesson, this vertical line is read given. So what's the probability that you would prefer a Nerf war if we're only looking at people over 10? Now remember, when you have a given probability, that means we're not looking at everyone. We're changing this total number of people. We're only looking at people over 10. And so people over 10, we don't have 108 of them. People over 10, we've only got 60 of them that we surveyed. So now we're out of 60, and out of those people over 10, those 60 people, 45 of them would prefer to have a Nerf war. And so this is 45 out of 60. And again, you could either simplify this or change it to a decimal. I'm going to change it to a decimal. And if you do 45 divided by 60, you get 0.75. Now, here's the information that we need in order to see if this is true. So let me phrase this as a question, kind of. Did it make a difference if you were over 10 or not, or if we just looked at everyone? Was it the same probability that you prefer to have a Nerf war, whether you're over 10 or just looking at everyone? It's 0.75, 0.75. Now, if these numbers came out to like real close to the same, but not exactly the same, you could probably still have a good argument that these are independent. If they came out a good bit different, you would say, yes, the one thing had an effect on the other. Now, keep in mind what our definition of independent was. You're saying the one thing happening had no effect on the other thing's probability. So, did being over 10 have any effect on the probability of liking to have Nerf wars? Well, there's a 75% chance you like to have Nerf wars if we just look at everyone. If you only look at people over 10, still a 75% chance that you like to have Nerf wars. That means there is no change in the probability. That means being over 10 had no effect on your preference for having Nerf wars. So, are these independent? Yes, they are. Independent means they do not affect each other, right? And so these don't affect each other. Now, this isn't the only way you could do this problem. You could also say, look at this for people over 10, look at this for people under 10, which, by the way, if you go with the under 10 column, you'll get 36 over 48. And to NERF or to total, 36 over 48 still comes out to 0.75, exactly the same percentage or decimal, which means that would also be the same. So being over 10 or under 10 has no effect on your preference for NERF or, since they don't affect each other's probabilities. That's independent. So something we could get as a result of this, kind of like a formula that goes along with this. For independent events, A and B, the probability of B given A is just the probability of B. Now, I know there's a lot of symbols and stuff going on in that sense, but if we really break down what these things mean, this is a really sensible observation. The probability of this happening, if you know this happened, is really still just the probability of that happening. Because being independent means this has no effect on the probability of B happening. So this happening is completely irrelevant, really is what you're saying. A happening, we don't care if it happened or not, it has no effect on the probability of B. They don't affect each other's outcomes. That's what it means to be independent. And so A happening has no effect on the probability of B. All right, so that's how we can determine if things are independent based on a two-way table and looking at the probabilities, basically seeing if one thing affected the other when we make that change.